first glance, this looks like the violent end of an offshore platform, 18,000 tons of steel collapsing into dust. But the real story begins long before the blast. These giants were built to survive 20-meter North Sea waves, decades of salt water, and loads heavier than entire buildings. Retiring them means doing the opposite, making something designed not to fail exactly as planned. Some platforms weigh 27,000 tons. Some jackets rise like steel skyscrapers from the seabed. And before one piece can move, ROVs inspect hidden connections, diamond wires cut through underwater steel, and engineers calculate how thousands of tons will behave when the sea is still moving. Then comes pioneering spirit, a vessel so massive it can wrap around a platform and lift entire topsides in a single operation. This is not demolition. This is controlled engineering at the edge of the ocean. This is what happens when engineers deliberately make an 18,000-ton offshore structure fail. Not by accident, but by design. The explosion is only the visible moment. The deeper problem is how to retire platforms built to survive North Sea storms, salt water, and decades of heavy loads. To recover the steel, crews must weaken something designed not to fail, while keeping the collapse controlled enough to turn demolition into part of the circular economy. These demolition shots are dramatic, but they also reveal why the offshore industry needed a different answer. When a platform is broken down piece by piece, every cut, every lift, and every drop has to be planned around risk. The steel is old. The joints may be corroded. The structure may have spent 20, 30, or even 40 years under wind, salt water, vibration, and changing loads. Even after production ends, the platform does not become simple. It becomes a giant industrial puzzle. Some offshore topsides weigh more than 20,000 tons, heavier than 3 Eiffel Towers worth of steel. Some jackets rise over 150 meters from seabed to deck. On land, sections can be dismantled in controlled conditions. Offshore, the same work becomes slower, more expensive, and more dangerous. This is the problem pioneering spirit was built to change. Not by making demolition more violent, but by removing the biggest sections before they have to be cut into hundreds of smaller pieces at sea. A controlled blowdown looks sudden, but the real work happened long before the structure moved. Engineers study how thousands of tons of load will travel, which members must release first, and where the platform is allowed to fall. The goal is not chaos. The goal is a predictable failure. That is the strange logic of decommissioning. A structure built to withstand decades of North Sea storms has to be turned into a structure that fails exactly as planned. Even a smaller part, like a helipad, shows how careful this work must be. It may look like one flat deck, but it is tied into beams, braces, walkways, and safety systems spread across a structure weighing many thousands of tons. Before removal, crews must separate it without sending unwanted loads into the remaining frame. This is why old offshore platforms are dismantled in stages. And the larger the section becomes, 10,000 tons, 15,000 tons, or more. After nearly half a century in the North Sea, Brent Charlie was no longer just an offshore platform. It was a piece of industrial history. For decades, platforms like this produced oil and gas in one of the harshest marine environments on Earth. They carried processing equipment, living quarters, pipework, electrical systems, cranes, flare structures, and heavy steel decks designed to keep working far from shore. But when production ends, the real engineering problem changes completely. A platform that once had to stay fixed against storms now has to be disconnected. A structure designed to carry thousands of tons safely for decades now has to be lifted, separated, transported, and dismantled. And every part of it has aged differently. Some steel members may still be strong. Others may have suffered corrosion, fatigue, or hidden damage. Some pipes may be empty. Others may need cleaning or isolation. Some modules can be removed in large sections. Others have to be stripped down more carefully before they can be moved. This is why bringing Brent Charlie home was not simply a towing job. It was a reverse construction project. Engineers had to understand the platform almost like doctors reading an old body, where the loads travel, which parts still carry weight, which connections can be released, and what must remain stable until the final lift. The most important idea is this: a platform does not become easy just because it has stopped producing. In many ways, it becomes harder. During operation, the structure has a clear purpose. During decommissioning, it becomes a giant puzzle of safety, access, weight, weather, and sequence. And this is exactly the kind of problem that led to the creation of vessels like Pioneering Spirit. If the largest topsides can be removed in one piece, much of the most dangerous work can move away from the open sea and into a controlled yard on land. The lift itself may look like the main event, but the real achievement is turning an old, complex offshore facility into something that can be safely picked up. The TAPD fields show that this challenge is not limited to the North Sea. Offshore decommissioning is becoming a global industrial task. As oil and gas fields reach the end of their life, countries have to deal with platforms, pipelines, wells, and subsea equipment that were never meant to stay in the ocean forever. Here, the problem is not just removing steel. It is proving that the field can be made safe after production stops. Wells must be secured. Equipment must be cleaned or isolated. Marine conditions must be checked. Lifting plans must be approved. And every step has to respect both worker safety and the surrounding environment. For a country carrying out offshore decommissioning for the first time, the learning curve is steep. The industry has to combine offshore construction knowledge with demolition, marine logistics, environmental control, and recycling. This is why old platforms are not simply abandoned pieces of metal. They are responsibilities. They mark the end of one industrial cycle and the beginning of another. And the more fields reach this stage around the world, the more valuable it becomes to remove large sections cleanly instead of sending crews offshore for long, risky dismantling campaigns. Brent Alpha makes the scale of the problem even clearer. At 27,000 tons, this is not a structure that can simply be cut apart without a plan. It is a giant assembly of steel, equipment, pipe racks, decks, and support frames, all built to work as one system while standing far out at sea. To deconstruct something like this, engineers first have to break the platform down on paper. They identify modules, lifting points, hazardous areas, access routes, temporary supports, and the order in which each section can be removed. The sequence matters because every removed piece changes the way the remaining structure behaves. That is the hidden difficulty. Demolition is not only about taking weight away. It is about taking weight away without causing the rest of the structure to move, twist, or overload unexpectedly. On land, the job becomes more controlled, but not simple. Large modules still have to be placed, supported, cut, cleaned, sorted, and recycled. Heavy machines can tear through steel, but they cannot replace the engineering decisions that happen before the first cut. Crews have to know what they are cutting, what it is connected to, and what could happen when that connection disappears. This is also why single lift removal became such a breakthrough. Traditionally, crews would spend months offshore cutting apart aging topsides section by section, often while standing inside structures that had endured decades of storms, corrosion, vibration, and fatigue. Every cut introduced uncertainty. Every lift depended on weather. Every extra day offshore increased exposure to risk. Single lift removal changes that equation. Instead of dismantling a giant platform piece by piece in the open sea, engineers can detach the entire topside, sometimes weighing tens of thousands of tons, and carry it back to shore in one operation. The work does not disappear. But the most hazardous phase is dramatically shortened. The yard then becomes the second battlefield. Here, the giant steel mass can finally be opened up. Pipework is stripped away. Equipment is removed. Hidden connections are exposed. Components are inspected after decades of service. Valuable metals are recovered. Hazardous materials are isolated and handled under strict controls. What once functioned as a self-contained offshore factory is gradually taken apart until it becomes streams of reusable material. Brent Alpha reveals one of the most important truths in decommissioning. Removing a platform from the sea is not the end of the story. It is only the moment when the story changes location. The real ending comes later, when thousands of tons of steel, machinery, and infrastructure have been safely dismantled, sorted, and returned to industry. The Campbell platform adds another layer to the challenge: geography. Every offshore platform occupies its own corner of the ocean, with unique water depths, weather systems, seabed conditions, vessel access constraints, and distances from support ports. What works in one field may become impossible in another. That means no two removals are ever truly identical. Engineers cannot simply pull an old plan from a shelf and repeat it. They must study the platform's condition, the available vessels, lifting capacities, tow routes, seabed hazards, and receiving facilities. Even a relatively small structure can become a major engineering problem if corrosion has weakened key members, access is restricted, or the weather window is measured in hours rather than days. This is why decommissioning is often described as reverse installation. When the platform was built, every component arrived in a carefully planned sequence. Removal follows the same logic, but in reverse. The difference is that the structure is now decades older. Steel may have aged. Modifications may have accumulated. Documentation may be incomplete. The half-weg platform shows that decommissioning is not a single dramatic lift. It is an industrial chain stretching from the offshore field all the way to the recycling yard. From a distance, people see a platform disappear from the horizon. What they do not see are the months, or years, of preparation hidden behind that moment. Before anything can move, the platform must first be made safe. Production systems are shut down. Residual hydrocarbons are removed or controlled. Electrical systems are isolated. Pipelines and risers are disconnected. Equipment that once handled enormous volumes of oil and gas must be transformed into something that can be safely dismantled. Only then does the platform begin its second life, not as a facility, but as a load. That transition sounds simple. In reality, it is one of the most technically demanding parts of the project. A working platform is a network of interconnected systems. A removable platform is a giant object whose behavior must be predicted with precision. Engineers need to know exactly where its center of gravity lies, how loads travel through the structure, which members are carrying critical forces, and how the platform will react when lifted by cranes or transport vessels instead of standing on its original foundation. Get those calculations wrong, and thousands of tons of steel may behave in unexpected ways. Then there is the sea itself. Weather is not just an inconvenience offshore. It is a design constraint. Wind, waves, and current can rapidly transform a routine operation into a dangerous one. A narrow weather window may determine whether a lift proceeds or waits for weeks. That is why so much effort happens before the vessel even arrives. Structural surveys, laser scans, engineering calculations, rigging design, cutting plans, contingency procedures, emergency scenarios. The visible lift may last hours, but the invisible preparation behind it can take months. When the platform finally moves, the operation often appears surprisingly calm. That calmness is engineered, A successful removal should not look dramatic. The structure is separated, lifted, secured, and transported according to a sequence designed to eliminate uncertainty step by step. Every completed stage reduces the risks facing the next one. Yet reaching shore does not mean the challenge is over. In many ways, the most visible destruction begins only after arrival. Massive steel sections are placed on land. Heavy machinery tears through decks and support frames. Equipment is removed. Materials are sorted. Reusable components are recovered. Contaminated materials are isolated and processed separately. This is where the scale becomes tangible. An offshore platform may contain thousands or even tens of thousands of tons of steel. What once stood above the sea as a complex industrial facility is gradually reduced to piles of material destined for recycling, reuse, or disposal. This is also where the circular economy stops being a slogan and becomes an engineering process. Every tone recovered is a tone that does not need to be produced from raw resources. The Halfweg project also helps explain why vessels like Pioneering Spirit matter so much. Such vessels do not eliminate decommissioning. They relocate the most difficult parts of it. Instead of exposing crews to long offshore dismantling campaigns, engineers can remove enormous sections in a single operation and transport them to shore. The dangerous separation still happens at sea, but only where absolutely necessary. That shift changes everything. Offshore, every hour is expensive, weather-dependent, and operationally complex. Onshore, the work remains difficult, but crews have stable ground, heavy equipment, controlled access, and far greater flexibility. So when people watch a platform being lifted in one piece, they are seeing more than an impressive feat of lifting power. The topsides are only half the story. Beneath them stands the jacket, the immense steel framework that has spent decades resisting waves, currents, storms, and the relentless forces of the sea while transferring the platform's weight into the seabed. A jacket presents a completely different engineering challenge. It may contain no processing equipment, but it is enormous, awkwardly shaped, and deeply embedded in the offshore environment. Its members may be covered with marine growth. Its coatings may be decades old. Its joints may carry the accumulated fatigue of millions of wave cycles. When a jacket finally arrives on shore and is laid down, its true scale becomes visible. What looked like a distant support structure offshore suddenly resembles the skeleton of a steel skyscraper. The B-11 platform illustrates the final objective of the entire process: removal, recovery, and renewal. After the offshore lift, after the transport voyage, and after arrival at the dismantling yard, the platform begins a transformation. Its productive life is over, but its material life is not. This is where decommissioning becomes more than a technical procedure. It is the closing chapter of an industrial asset that may have operated for decades. It is the removal of infrastructure that once generated energy far from shore. And it is the recovery of enormous quantities of steel and equipment that can re-enter industrial supply chains. The time-lapse footage makes the work appear effortless. In reality, every movement is controlled. Giant sections are positioned carefully. Heavy machines cut through thick steel. Crews manage stability, access, lifting hazards, and exclusion zones. Piece by piece, the platform disappears. Not because it is being destroyed, because it is being transformed. And that raises an unavoidable question. If dismantling offshore structures is already one of the largest engineering cleanup projects in the world, before a platform can be lifted, engineers often have to deal with the equipment around it. A loading buoy may look much smaller than a full offshore platform, but it is still part of the same industrial web. Pipelines, mooring systems, transfer equipment, and steel structures that once moved oil from the seabed to ships. Removing it is not just a matter of pulling it away. Crews must secure the buoy, control its movement, disconnect old systems, and bring it back to shore without losing control of the load. The Capal field shows the same idea in a different offshore environment. Decommissioning is never a single universal recipe. Each field has its own water depth, weather, marine traffic, seabed layout, and condition after years of operation. That means the first job is always understanding what is really there. Before crews remove equipment, they need surveys, lifting plans, vessel coordination, and a clear sequence for how each piece will be disconnected. A platform may look isolated from above, but below the surface it is tied into a much larger field system. Not every offshore structure is removed in the same way. In some places, old jackets can become artificial reefs, creating habitat for marine life. It is a different ending, but the engineering question remains the same. What should be removed? What can remain? And how can the sea be protected? This is where the underwater work becomes visible. A work-class ROV uses a jetting tool to clear marine growth, sediment, or debris around offshore equipment. To the viewer, it may look like simple cleaning, but for engineers, visibility is information. Before a cut, a lift, or an inspection can happen, the connection has to be exposed. Bolts, welds, braces, and pipeline interfaces must be seen clearly enough to judge their condition. Underwater, even cleaning becomes part of the engineering sequence. ROVs are the eyes of the decommissioning team. They inspect anchor lines, pilings, moorings, tanks, and submerged structures without sending divers into every hazardous location. That matters because offshore removal depends on confidence. Engineers must know what is still connected, what has deteriorated, and which parts are safe to cut or lift. A smaller ROV can still answer big questions. It can move around jacket legs, braces, risers, and mooring points, recording details that are impossible to judge from the surface. These surveys help turn uncertainty into a plan. They show where marine growth is hiding steel, where corrosion may exist, and where the structure must be cleaned before removal begins. When a structure cannot be lifted whole, it may have to be cut underwater. Diamond wire cutting is one method used for controlled subsea modification and decommissioning. The principle is simple to understand. A strong cutting wire is guided around the steel or concrete section, then driven through it with controlled force. But offshore, the execution is anything but simple. The tool must stay aligned. The cut must finish cleanly. The release section must not move unpredictably. This is the hidden preparation behind the spectacular lift. Before a giant topside can rise in seconds, the ocean floor must be surveyed, cleaned, disconnected, and made ready. Now the reason for all that preparation becomes clear. Here, pioneering spirit removes the Eider Alpha topsides from the northern North Sea in a single lift. The structure weighs more than 11,000 tons, yet the most visible moment is surprisingly short. The vessel moves in, positions itself around the platform, takes the load, and carries the topsides away. But the speed is almost misleading. This lift is only the final second of a much longer engineering process. Years of planning, months of offshore preparation, structural checks, cutting work, motion control, and a carefully timed transfer of load from the old platform to the ship. Pioneering Spirit was not designed like a traditional crane vessel. Its most important feature is not a single towering crane. It is the shape of the ship itself. The vessel uses a twin-hull design with a wide slot at the bow. Instead of sitting beside the platform and lifting from one side, it can move around the structure. The topsides sit between the two bows, and the lifting system reaches underneath the platform from both sides. That changes the whole logic of offshore removal. A normal crane lift concentrates enormous force through hooks, slings, and a lifting boom. Pioneering Spirit spreads the operation across a much wider system. Lift beams, yokes, hydraulic cylinders, motion compensation, ballast control, sensors, and dynamic positioning. The goal is not just to lift. The goal is to make the platform and the vessel behave like one controlled machine for a few critical seconds. Then ROVs took the idea further with the jacket lift system. The top sides are the upper industrial city. The jacket is the steel skeleton standing in the sea. Removing jackets used to require cutting, lifting, and transport by separate operations. A dedicated jacket lift system gives pioneering spirit a second role, not only removing the top of a platform, but also handling the massive support structure beneath it. This is why the vessel is more than a ship. It is a mobile offshore removal system. Even installing the lifting system becomes a mega engineering project. These beams are not small attachments. They are massive structural tools, added to the vessel so it can handle entire offshore jackets. In this topsides removal, the same principle appears again. The platform section is not slowly dismantled offshore. It is prepared, released, lifted, secured, and carried away as one enormous load. That is the power of single lift removal. It reduces the time crews spend cutting heavy structures at sea. It also moves much of the dangerous dismantling work to shore, where equipment, access, and safety control are far better. But pioneering spirit did not appear from nowhere. It belongs to a much larger offshore engineering world, where vessels are built to perform industrial work far from land. Solitaire is a good example. It is not a platform removal vessel, but a giant pipelay ship. Its job is to carry, weld, and install heavy pipelines across the seabed while holding position with extreme precision. That connection matters. Whether a vessel is laying pipe or lifting a platform, the hardest offshore problem is often the same: controlling huge forces on a moving sea. The ship must know where it is, hold position, manage load, and keep the operation stable while wind, waves, and current are constantly trying to move it. Pioneering spirit takes that offshore construction logic and applies it to one of the heaviest removal problems on Earth. To understand why pioneering spirit matters, we have to look beyond oil platforms. Modern offshore engineering is no longer only about drilling for oil and gas. It is also about building enormous energy systems at sea. Offshore wind farms, converter stations, subsea cables, pipelines, and old platforms all share one problem: the most important work happens far from stable ground. Mate shows that challenge clearly. Each monopile foundation is a giant steel tube driven into the seabed to support a wind turbine. It must be designed, fabricated, transported, lifted upright, positioned, and installed with very little room for error. The components are so large that even the logistics become part of the engineering. A port becomes a staging yard. A vessel becomes a mobile crane base. The seabed becomes the foundation line. And every movement depends on weather, wave, height, vessel position, and lifting capacity. This is the same offshore world that produced pioneering spirit. Whether engineers are installing wind turbine foundations or removing an aging oil platform, the core challenge is not just size, it is control. Huge steel structures must be moved safely in an environment that is always moving. That is why offshore vessels are becoming less like ships and more like floating construction systems. When a pipeline or heavy subsea structure reaches the seabed, engineers must know exactly where it touches down. Touchdown monitoring turns an invisible underwater moment into data. Survey systems, cameras, sensors, and positioning equipment help crews see the shape of the pipeline as it leaves the vessel and settles toward the ocean floor. Without that feedback, a controlled installation becomes guesswork. Before a pipeline ever reaches the sea, it has to survive the sea. That begins in the coating plant. Bare steel pipe is cleaned, prepared, heated, and covered with protective layers. A three-layer polyethylene coating is designed to protect the pipe from corrosion and mechanical damage once it is buried, lowered, dragged, or exposed to seawater. This may look like a factory process far removed from pioneering spirit, but it is part of the same offshore chain. A pipelay vessel can only work efficiently if every pipe joint arrives ready. The steel must be dimensionally correct. The coating must bond properly. The ends must be prepared for welding. And every defect found on land is one less problem to fight offshore. Some offshore pipelines need more than corrosion protection. They also need weight. Concrete weight coating adds a thick, heavy layer around the steel pipe. This helps the pipeline resist buoyancy, stay stable on the seabed, and remain in position under waves, currents, and seabed movement. The process is simple in concept but demanding in executions. The concrete must be applied evenly around the pipe. The thickness must be controlled. The finished pipe must still be handled, stacked, transported, and welded later without damaging the coating. This is why pipeline construction is not just one operation at sea. It is a long industrial sequence. The factory prepares the pipe. The coating gives it protection and stability. The supply chain moves it to the vessel. Then the offshore crew welds each section into one continuous line and lowers it into the sea. S-lay pipeline installation gets its name from the shape the pipe forms as it leaves the vessel. From the firing line on deck, the welded pipe travels backward, passes over a support structure, curves down through the water, and finally touches the seabed. That long curve is the danger. If the pipe bends too sharply, it can buckle. If it is not supported correctly, the steel can be overstressed. If the vessel moves out of position, the touchdown point can shift. So the operation becomes a balance between welding speed, vessel movement, tension control, seabed conditions, and real-time monitoring. On deck, crews handle pipe joints, align ends, weld, inspect, coat the field joint, and move the pipeline forward. Under the vessel, the sea is constantly trying to turn that controlled curve into a problem. This is why a pipelay vessel is not just carrying pipe. It is managing a continuous steel structure that may eventually stretch for hundreds of kilometers across the seabed. On board Pioneering Spirit, the idea of a floating factory becomes literal. The vessel does not simply pick up pipes and drop them into the ocean. It turns pipe installation into a continuous production line at sea. Supply vessels bring pipe joints alongside. The pipe is transferred on board, moved into position, prepared, aligned, welded, inspected, coated, and then fed into the water in a controlled sequence. Every station has a purpose. Pipe ends have to be cleaned and prepared so the weld can form properly. Alignment is critical because even a small mismatch can create a weak point in a line that must survive pressure, temperature changes, seabed movement, and corrosion over many years. After welding, the joint is inspected. If a flaw is found offshore, the entire rhythm of the operation can slow down. Then comes field joint coating. The factory-applied coating protects most of the pipe, but each welded connection creates a gap that must be protected after welding. That means the vessel also carries equipment to restore protection around every joint before the pipeline disappears into the sea. The final step is lowering. This is where Pioneering Spirit's size and control matter. The pipe is not just dropped, it is guided. Tension must be maintained. The angle must be controlled. The vessel must hold position while the pipeline extends farther and farther behind it. This process helps explain why the same company could build a vessel capable of lifting oil platforms. Pipelay and platform removal may look different, but they share the same engineering language: heavy steel, precise positioning, controlled load transfer, and constant motion compensation. In Pipelay, the load is a long, continuous pipeline. In topsides removal, the load is a massive platform section. In both cases, the ocean is not a passive background. It is an active force pushing against the operation. That is the deeper point. Pioneering Spirit was not built only to be big. It was built to make large offshore operations repeatable, controlled, and safer. It carries the logic of a factory into a place where factories normally cannot exist. The vessel becomes the worksite, the transport system, the lifting machine, the control room, and the production line at the same time. And that is why its role in decommissioning is so powerful. If it can manage a continuous pipeline at sea, it can also manage the controlled transfer of an entire platform topsides from a fixed structure onto a moving vessel. A wider view of offshore Pipelay shows just how many operations must work together at once. On the surface, the vessel appears to move slowly. But inside that slow motion is a chain of highly timed tasks. Pipe joints are brought forward. Welding stations operate one after another. Non-destructive testing checks the weld quality. Field joint coating protects the exposed area. Tensioners grip the pipe. The stinger supports its curve. Survey systems monitor the route and touchdown point. If one stage stops, the entire line feels it. That is why offshore construction rewards reliability. The vessel may be hundreds of kilometers from shore. Spare parts, weather windows, crew shifts, supply vessels, and inspection teams all become part of the schedule. A delay is not just lost time. It can mean missed weather, extra vessel days, and greater exposure to risk. This is also why footage of offshore pipelay is useful in a story about platform removal. It teaches the viewer how engineers think at sea. They do not only think about the object being moved, they think about the system around it. The vessel, the load, the support equipment, the seabed, the data, the weather, and the people who must make decisions while the operation is already underway. The same thinking applies when Pioneering Spirit approaches an old platform. The topsides are a load. The vessel is the support. The sea is the moving environment. Sensors provide information. Thrusters hold position. Hydraulic systems control motion. And the lift can only happen when all of those pieces agree. Pipelay looks slow because it has to be controlled. Platform lifting looks fast because the final motion happens in seconds. But both are built on the same foundation: months of preparation, thousands of checks, and a vessel designed to turn offshore uncertainty into a manageable sequence. Before offshore pipelay begins, the pipeline starts as manufactured steel. Spiral welded pipe is formed by feeding steel plate or coil into a forming machine, bending it into a cylinder, and welding the seam as the pipe takes shape. This method can produce large diameter pipe efficiently for industrial and infrastructure use. The important point is continuity. A pipeline is only as strong as the quality of its steel, welds, coating, inspection, and handling. By the time a pipe joint reaches an offshore vessel, many critical decisions have already been made inside the factory. When pioneering Spirit prepared for her first Pipelay job, the scale of the vessel showed why it was such a radical step in offshore construction. This is not a ship built for one narrow task. It is a huge working platform long and wide enough to carry heavy equipment, pipe handling systems, welding stations, lifting systems, power generation, accommodation, control rooms, and marine machinery in one moving structure. That size creates possibilities. A larger deck gives engineers more room to organize the production line. More power supports heavier systems. A wider hull gives stability. Dynamic positioning keeps the vessel where it needs to be without anchors that could interfere with subsea infrastructure. But size alone is not enough. The vessel also has to be organized. Every station must feed the next. Pipe must move smoothly. Welding and inspection must keep pace. Crew access must be safe, and the ship must hold position while the pipeline is gradually built behind it. This is offshore construction turned into industrial choreography. Darwin Kappa brings the story back to heavy lifting. An offshore converter station is not an oil platform, but it faces many of the same installation challenges. It is a giant industrial structure placed at sea, filled with equipment, supported by a jacket, and connected to a wider energy network. For offshore wind, converter stations collect and transform power before sending it back to shore. That makes them essential pieces of the new energy system. Installing one is a major lift operation. The topsides must be transported offshore, positioned over the foundation, aligned carefully, and set down so loads transfer correctly into the jacket. The structure is huge, but the final fit depends on precision. This is why the same vessel logic matters across different industries. Pioneering Spirit can remove old oil and gas infrastructure, lay pipelines, and help install new offshore energy systems. It is not just a tool for the past. It is part of the transition from one offshore era to another. A ship built to retire old platforms can also help build the next generation of offshore infrastructure. Before anything massive can be installed offshore, it must first survive the port. These wind turbine blades and tower sections show the first stage of heavy offshore logistics. The components are already enormous on land, long before they reach the sea. Quaysides, storage yards, transport routes, lifting gear, and timing all have to match. At this scale, logistics becomes engineering. Once the components leave port, the ocean becomes the real construction site. Offshore wind installation shows the same engineering language that appears in platform removal. Foundations must be positioned. Towers must be lifted upright. Nacelles and blades must be installed high above the water. The vessel must hold position while every major part is suspended, aligned, and secured. Nothing here is small. A single blade can be longer than the wingspan of a large aircraft. A tower section can weigh hundreds of tons. A nacelle is not just a housing. It contains the machinery that turns wind into electricity. And the final assembly happens on a moving sea, where the window for safe lifting may be limited by wind, waves, and daylight. The installation vessel becomes more than transport. It becomes a temporary factory, crane base, hotel, control room, and precision platform at the same time. That is why offshore work always rewards preparation. The lift may look like the main challenge, but the lift is only possible because every earlier step has been arranged. Component delivery, sea fastening, vessel stability, lifting sequence, weather forecasting, crew coordination, and final alignment. This connects directly to pioneering spirit. Whether the job is installing a wind turbine or removing an oil platform, the same problem returns. How do you control huge steel structures in a place where the ground itself is moving? The answer is never one machine alone. It is the entire system around the machine. Here, pioneering spirit is not lifting a platform, it is laying pipe. But this scene helps explain why the vessel is so important. A pipeline may look like a long steel line, but at sea it behaves like a continuous load under tension. The vessel has to keep moving, keep welding, keep supporting the pipe, and keep the touchdown point under control. This is precision work disguised as slow movement. The same control philosophy later becomes essential when the vessel handles a massive platform topsides. The stinger is one of the least glamorous but most important parts of S-lay pipelaying. It supports the pipeline as it leaves the vessel and begins curving down toward the seabed. Without that controlled support, the pipe could bend too sharply, overstress, or buckle before it reaches its final position. Under the hull, another hidden system decides whether heavy offshore work stays safe: the thrusters. Thrusters are the muscles that help a vessel hold position without anchors. In dynamic positioning, they constantly adjust against wind, waves, and current. For a vessel lifting thousands of tons, position is not a background detail. Position is part of the lift. A thruster upgrade may not look as dramatic as a platform lift, but this is the kind of work that makes offshore precision possible. A vessel working in deep water or close to subsea infrastructure cannot always rely on anchors. It may need to hold station using azimuth thrusters, power systems, control software, sensors, and real-time positioning data. Together, these systems allow the ship to resist environmental forces and stay in the exact working zone. When thrusters are removed, rebuilt, upgraded, or tested, engineers are protecting the reliability of the entire operation. That matters because a heavy lift is not just vertical force. The load also has to stay aligned. If the vessel drifts at the wrong moment, the geometry of the lift can change. Clearances can close. Loads can shift. A controlled transfer can become dangerous. This is why the most important parts of a giant offshore vessel are often invisible from above. The viewer sees a huge ship. Engineers see propulsion redundancy, power distribution, control logic, and failure margins. If thrusters help control the vessel, hydraulic cylinders help control force. In heavy lifting, cylinders act like controlled muscles. They can push, pull, hold, compensate, and transfer load with enormous power. But their value is not only strength, their value is controllability. A hydraulic cylinder has to be machined accurately, sealed properly, assembled cleanly, and tested before it can be trusted in harsh conditions. The piston rod must move smoothly, the seals must hold pressure, the cylinder body must resist internal loads. Any weakness can become a serious problem when the equipment is working offshore. For pioneering spirit, this kind of technology is central. The topsides lift system depends on hydraulic control, not just brute force. The vessel must take the load in a controlled way, while the sea is still moving beneath it. This cylinder rebuild shows why hydraulic reliability is built one detail at a time. From the outside, a cylinder looks simple: a metal tube, a rod, and hydraulic connections. But inside, everything depends on surfaces, seals, clearances, lubrication, and pressure. If one seal is damaged, the cylinder may leak. If a rod is scratched, it can destroy the seal again. If contamination enters the system, it can damage internal surfaces and reduce control. That is why rebuild work is careful. The cylinder is opened, cleaned, inspected, resealed, reassembled, and tested. Each step restores the ability of the cylinder to hold pressure and move predictably. For a small machine, a leak might stop a job. For a giant offshore lifting system, a loss of hydraulic control can affect the entire load path. This is the important connection. When pioneering spirit lifts a topsides, the operation is not one giant yank upward. It is a coordinated transfer of weight. Hydraulic systems help absorb motion, share load, and control how the structure separates from its old support. The goal is not only to lift high enough, the goal is to lift evenly enough. Imagine a platform topsides sitting on its jacket after decades at sea. The steel has weight, the sea is moving, the vessel is moving. The old support structure may not release perfectly at every point. If one side takes load too quickly, stress can concentrate. If another side lags, alignment can suffer. Hydraulics help manage that moment. They turn a violent-looking operation into a controlled mechanical sequence. Pressure, stroke speed, and load can be monitored and adjusted. In some systems, accumulators can store energy and help smooth sudden changes. Motion compensation can reduce the effect of wave movement. Sensors can tell engineers whether the load is transferring as expected. So this workshop footage is not a detour. It shows the small-scale truth behind mega engineering. The largest offshore machines depend on components that must work perfectly inside. A massive lift beam is useless if the cylinders cannot be trusted. A giant vessel is vulnerable if its control systems cannot hold force, and a spectacular lift in seconds is only possible because countless mechanical details have already been tested long before the vessel reaches the platform. Offshore wind turbine installation brings the same lesson back into open water. The machine is enormous, but the final fit is precise. Tower sections must land on their flanges, bolts must align, blades must be handled without damage. The nacelle must be positioned high above the sea while the vessel moves below. This is why offshore installation vessels are designed around stability, jacking systems, cranes, lifting plans, and weather limits. The operation looks like construction, but it feels closer to surgery at industrial scale. That same mindset applies when pioneering spirit removes a platform, move the giant object, but control the millimeter scale consequences. An offshore converter platform shows how large offshore structures are changing purpose. Instead of producing oil and gas, these platforms collect power from wind farms, convert it, and send it back to land. They can be as tall as a building and nearly as large as a football field. But the engineering challenge is familiar. A massive topsides must be fabricated, transported, lifted, aligned, and connected to its support structure. Whether the platform handles hydrocarbons or electricity, the sea demands the same discipline: weight control, load transfer, positioning, and precision. These 5,500-ton beams reveal something important about pioneering spirit. Even the tools added to the vessel are themselves megastructures. A jacket lift system cannot be treated like ordinary equipment. The beams must be transported, aligned, lifted, and installed onto the vessel with extreme care. Their job is to carry enormous loads later, so their own installation must be accurate from the beginning. In other words, before pioneering spirit can lift giants from the sea, engineers first have to build giant lifting tools into the ship. The story also returns to fabrication. Large offshore vessels, platforms, and lift structures all begin with welded steel. A panel welding gantry uses automation to weld large shipyard panels with repeatable motion and controlled paths. Based on digital models, the system can plan welds across horizontal, vertical, and transverse seams. This matters because offshore strength is created long before the vessel meets the sea. Every beam, deck panel, and structural box depends on weld quality. A poor weld is not just a workshop defect. In a heavy lift, it can become a weak point in a massive load path. Precision fabrication is the first layer of safety. Steel box girder fabrication makes the same principle easy to see. Large steel structures are built from plates, seams, internal stiffeners, and carefully controlled welds. Whether for a bridge or offshore equipment, strength begins inside the workshop. In the end, the platform does not simply disappear. Its steel is cut, sorted, loaded, and sent back into the industrial chain. The offshore structure becomes material again. The lift may last only seconds, but the real achievement is completing the full circle: removal, dismantling, recycling, and responsibility.